right, the time is 12:30 sharp. I make an attempt to put something on the website half an hour ago. So the lecture from last Tuesday and today's lecture must be there. Okay. The rest is irrelevant stuff that I'm going to be correcting when I have time. Okay. And I think probably tomorrow I'm going to email those registered some chapters from books to read. Let's see, another announcement. We're going to post an early homework, but it's not going to be due for another 3 weeks or so. But I want you to just know what is coming and to start reading. And in the process of the homework, we're going to have recitation tomorrow. So Suvi can introduce you to basically review what we have done, introduce you maybe to some programming aspects for probabilistic graphical models, because I think the way he's preparing the homeworks, he wants you to start building little libraries that eventually will lead to large-scale problems. Now, if you don't manage to develop these libraries in homework 1, we're going to post the solution so you can use on the second part ours. But trust me, whatever we post doesn't mean it's the right thing. I mean, we are also students and we post whatever, so hopefully you can do better than us, and hopefully the solutions we post are your solutions. That's why I want you to type them, right? Cut and paste. Okay, and what was the other announcement? And so in this process, we're going to have a recitation this Friday, but as I told you, the recitation, the same way as the lectures, are not mandatory. So if you don't like to see me, you don't have to come. You know, there are video lectures, everything is online. You can watch me from your kitchen, basically, while having a cup of coffee. But there's going to be a recitation at the same time on Friday, and again, not mandatory, because all the information will be posted. And so the homework, the lectures, okay, so you will notice when you review the slides from lecture 1 that there are some topics that I did not cover, okay? Now those topics are really sort of a little bit more examples on the concepts that I was trying to communicate. Some of them are going to come in this lecture, so I don't have to do them. Some maybe Sudik will cover on Friday. Some you have to read them on your own, okay? And but if there is anything essential, I will go back to it, okay? If I don't cover it, it means we don't really need it, but it's helpful. So for example, there is a big case study of a probabilistic graphical model related to biology. And as you guys told me, there's nobody from biology. Actually, I was asking yesterday a colleague of mine, I said, do you have any students in biology doing this type of things? Like, no, sorry. You know, so I don't know if I start talking for 20 minutes today on biology, and I did prepare all the slides, maybe a third of you may switch to biology, and that is not going to be good, right? Or the other way around. Okay, so we're going to start discussing a little bit about conditional independence relations and graphs, but even in the context of the theoretical aspects of these conditional independence relations that the graphs represent, this is sort of an introduction. So we will formally go back to it again and again for the next maybe 2 weeks, so we have a very rigorous understanding. So treat, if you get the concepts today, the lectures following up will be easy, but you don't have to understand everything. Okay, so if you remember, I introduced basically, this is the product rule of probability. If you have V variables, assuming absolutely zero independence relations, this is a factorization that is generic. All right, so look at it carefully. All right, and P of x1, x2 given x1, x3 given x2, x1, and I can write several decompositions like that, because, for example, I can start with x2, and then x1 given x2, then x3 given, x1 and x3, etc., etc. So in essence, I have various of those, and in some way they're not symmetric, right? The way that I write them, there's nothing that shows any sort of symmetries here. Okay, this expansion is very expensive to do. So if you just look on this, if you have, let's say, k values for each variable x, and you have v of those, so this will require a table of the order of k to the power v. And this is the reason really we study probabilistic and graphical models, because we will be asking questions such as, can we actually simplify these conditional distributions accounting for some independence relations? In other words, looking at this, is really explore, given x1 depends on x2 and x3, can I get rid of x2 and x3? If the answer is yes, we will be able to have a factorization that is very efficient. So this count that I did here does not account for normalization of each of these probabilities, which is really, it doesn't remove much of the cost. And so when you look at P of x1, you need k numbers to describe it, k squared to describe x2 given x1, k cubed to describe this, and k to the power v basically to describe them. Now, for those who study machine learning, right, if you have a distribution like that and you want to use it in the context, let's say, of classification problems, there's a lot of tricks you can do, but you don't have to deal with complexity of k to the v. And so here's one example. Rather than making tables for each of these conditional probability distributions, what you do is you replace them with a multinomial logistic regression model, which looks like that. All right, so each of these distributions that you see here, it's so t can go from 2, let's say, to v, depends on all the previous x's. So I try to fit this distribution to some sigmoidal function with an argument of some matrix w times the vector x of all the previous values. And again, you may have not seen this, but this is sort of a nice model. So this is a sigmoid function, and to fit this probability, we take the k component of the argument, and there is a nice model for this conditional probability for any of them, and you will not have to fix a table to describe them. Okay? Now, it comes out that the cost of this model, and I have the calculation here, so if anybody has any questions on how I get it, it's actually straightforward. You may want to do the algebra to convince yourselves. So it comes out that the cost of this is k times v squared. Before the cost was k to the power v, now it's k to v squared. So it's really, I mean, it depends of course what v is, but it is significantly reduced from that cost. Okay? However, this model is not very useful, right? Because each of these conditional distributions depends on the values of all the other previous variables. So you will not be able to do much beyond sort of use this in the context of a classifier. So if you want to do predictions and you want to find marginals, account for evidence and things like that, you will not be able to do the algebra using this model. Okay? But again, the idea of this model is rather than having tables to describe this, fit some function, all right? And in this case, what you will need to do is compute this matrix W, and once you have it, then this would be an easy problem to use in the context of classification. So we don't want to do this in this course. We want to do something better. So I'm going to introduce some basic things for probability, in case you have not seen them, that are related with marginal and conditional independence. So I have random variables x, y, and z, can be scalar, can be vector. So I say that x and y are conditionally independent given z, when p of x given y and z is equal to p of x given z. Okay? So if I know z, learning something about y doesn't make a difference when it comes to the value of x. Okay? So this is one way to write the conditional independence of x from y given z. This is important. That's why we say conditional, because there is an argument z there. Now, if you use this, if you take this as a definition, you can see the simple algebra, right? I can write this p of x given y and z, and then p of y given z. So using this, I can write this as p of x given z, p of y given z. So you can use as a definition, if you like, or as an alternative way, that when this conditional distribution factorizes like that, then x and y are independent conditional on z. Okay? So sometimes this will be convenient, sometimes this. They're exactly the same thing, basically. Okay. You can actually, and we will need this in our follow-up lectures, we will need to have this conditional independence relations only also in terms of sets of random variables. So we can write that a set of x of random variables is dependent on another set y given z, when x is independent of y given z for every x in the set x and every y in the set y. Okay? And actually this z I can make it also a set, so maybe that would have been even more generalized. We will see this in a graph. For example, we say this set of variables is independent of that given that set of variables, so this basically will follow this definition here. In the independence we use it with this sort of orthogonality condition, but in some probability books this orthogonality condition may imply something else, usually defined in terms of expectations. Okay? But for us this is the notation we're going to use. If you get rid of the dependence on z, marginal independence basically, if you take this definition, for example, means that p of x and y is given p of x, p of y. Okay? I noticed just looking at this slide, right, it helps to teach sometimes because I see, for example, I'm abusing the notation here in a violent way, but hopefully we can still get the message. For example, here I use capital X and Y for the variables, here little x and y. They're effectively the same things, but traditionally this will be the random variable and this will be the values the random variable can take, but we're okay, right? We're not going to say, oh sorry, you put a little x, It's good that I typed this slide, so at least we have some slides to talk about. But when you write papers, it's a good idea to sort of be careful and consistent, because it looks good when you're consistent. Okay, so 2 examples to communicate this message on this conditional and marginal independence. Okay, so given the speed of the car, I am saying here that the speed defined is independent of the type of the car. Conceptually, you understand that? Like if somebody goes with 100 miles an hour, right? Then let's say the probability of getting a fine is independent of what type of car he drives. Okay? But if you do this marginally, the speeding fine is not independent of the type of the car. I mean, if you drive a fancy car, you may have the tendency to drive faster, just so you can impress the girls on the street, right? So this sounds sort of a trivial argument, but in the context of directional graphical models is very essential, because it will define the causal relations that we can, and independence relations that we can postulate. So another example that's actually the opposite of this, if you have, let's say, 2 teams playing basketball or something, so the ability of team A marginally is independent of the ability of team B. Let's say that they're both, average teams, right? So marginally they're independent. But obviously, if you know the outcome of the game between A and B, you cannot say conditionally that A is independent of B, right? If A won, then you're going to say the probability of A is higher, is, I mean, A, you know, would be exactly the opposite effect from the first example. Okay, so this is the definition again. So what I'm going to do is here, you know, I'm writing, you know, this is a standard. We're going to spend actually 2 or 3 lectures discussing about this hidden Markov and state space models. But this is a Markov chain. So you can imagine, you know, you have some state variable, but and you look at the values of it with time. So x1 is the value at time 1, x2, time 2, etc. So I'm using a Markovian assumption here, where the value of x at time t depends only on the value at time xt minus 1. So compare this expression with the expression that we had. Remember, this was this long expression. Compare this, right, with this Markovian model that is very simplified, because xt doesn't depend on xt minus 2 or xt minus 3, etc. Okay? So this is this model basically assumes the independence relations, in particular that xt is independent, you know, given xt minus 1 is independent of all the previous values xt minus 2 to x1. Okay, so let me introduce you, starting early on this course, on something sort of I highlighted on lecture 1, which is, you know, introduce the parents of a node, right? So in this case, if we look at node V has 2 parents, okay? And so I want to introduce a fundamental independence, conditional independence relations for this directed graph. And so let's read what it says. xv is independent from the non-descendants of V given its parents. So there's a note there. So given the parents, to emphasize that the parents are given, this is highlighted dark blue, all right? So if I know the values of the parents, it says that the value of V is independent from the non-descendants. So if you think of topological order, the non-descendants will have numbers that they are basically anything above the values of the parents, basically, in the order, okay? These are the non-descendants, right? So if I know the values of the parents, xv is independent from the non-descendants. I am not proving or anything like that, right? So you, at this point, just want you to visualize as to what this means, because we will, I think we will sort of highlight the proof. It's not very difficult, but once you have this, the decomposition of the probability defined on this graph will be way too simplified, okay? So we will be able to take advantage of this relation. And in principle, we will show that any distribution that factorizes on this graph satisfies this relation, and for any distribution on the graph, this relation is also satisfied. You know, I mean, you can see, sorry, one way or another, all right? So both ways, this would be the correct argument. Okay. Using this relation, we will be able to show that the factorization of a joint probability on a directed graph is written as the product over all the nodes of the graph of the conditional probabilities of xi is the variable in node I, given the parents of I. This is an amazing decomposition if you think about it, right? So, you know, there is a function, in this case a conditional probability corresponding to its node, and this function is the conditional probability of xi given its parents. So any distribution that factorizes over this graph, because of this independent relation that we introduced, which is sort of identical, just different notation from the one I discussed, leads to this. Okay? So I will do examples, right? Some trivial examples and some a little bit more complicated.
but I want you to start thinking that, you know, this is great, and let's see how it works, and also let's see if we can prove it. But right now, I'm just telling you that as a conclusion and a fundamental property of directed graphs, the joint distribution factorizes over the nodes, and these factors here, these functions, are the conditional probabilities of xi given its parts. All right? Remember when we had this complicated factorization from the product rule, here we didn't only have the parents, we have the children and the co-parents and the non-descendants, everything else was coming there, but because of this independence relation, the only factors we get is xi given the parents of node I. So I'm actually, so here what I'm doing, I am taking a directed graph with 5 variables. The first equation writes the product rule, so no independence assumptions, I am assuming nothing. And then I am applying sort of this equation, right? I'm applying this equation that says that this distribution is factorized this way, and I'm writing it as the probability of x1, because x1 has no parents, all right? The probability of x2 given x1, that's the only parent, of x3 given only x1, x4 given 2 and 3, and x5 given 3. So immediately you can see the independence relations that are being used here. Because effectively what I say is that this probability is equal to that, which means that given x3, x5 is independent of what? I mean, looking at these two equations there, given x3, x5 is independent of x1, 2, and 4, right? And here, given x2 and x3, x4 is independent of x1. Here, given x1, x3 is independent of x2, etc. Now, you may say, how will I know, I mean, I give you a graph like that, right? But how, in a general graph, how will I know this independence relation? Well, we will spend a lecture or two, and we will, yep.
Cases in which we want to analyze our DAG using higher order?
So when we say it's first order, it's actually not first order, because you notice here it comes out that x4 depends on x2 and x3. It depends, so it's not really first order. So this is very general, actually. First order would imply that x4 depends only on x3, x3 only on x2, etc. Okay. So this is, so it's very general. It's not, so it's not a Markovian model. Okay? All right. So just looking at this equation, right? If each of these variables take k values, right? So let's say it's a discrete variable, and we have v of those. The cost basically, in general, is v times k to the power f. But right now, the cost is really, we have a v of these terms, so it is v times. What's the cost of this? So, in this case, of course, we need to decide how many parents we have. So, if the parents are f, right? So the cost will be k to the power f times v. Okay? And we will see actually a much more general expression, even for sort of undirected graphs, but right now, in the context of this, if let's say f is the number of parents, k to the power f to describe this times v. In principle, actually, somebody can say k to the power f plus 1. You see that? But, it's like if you account for the normalization and everything, so that's approximately the order. Why do you say k to f plus 1? Right? Because, this is going to take, not f plus 1. So this will take, this will take, okay, I have f of this, right? Each of them take k values, and I'm going to have this also taking k values. All right? So it is V times K, F plus 1, okay? But one F doesn't here, so I'm just accounting for the parents here. But you can take a note if you want on this. Let me just say that, when you guys program some of these things, you will find out that if you put the wrong ordering of the nodes in the graph, you may take a problem that is trivial and make it very difficult, right? Because everything depends on this topological order, but you start with some weird numbering, and then you find yourself that everything depends on everything, right? And so this is, I'm not going to go through this example right now, but maybe we will give you some of this for homeworks. This is sort of the five random variables. And you can see different orders, right? Which of these graphs you would like to play with? I mean, they're all the same, all right? But which one we have the minimal cost? And the key thing is that the left is your preferable because the left has what? Less what? Less edges. And if you remember edges, less edges means more independence relations. Okay, and this is what we're interested in. So this is something very complicated we don't like. Yeah, it says there, it is the absence of edges basically that's important, but because this indicates conditional independence relations. I'm going to highlight the proof of the decomposition on directed graphs. Actually, the proof is trivial, all right? But I'm going to highlight it, and you guys can spend 5 minutes to read the notes. Let's assume the following, that associated with every node in the graph and its parents, we assign some arbitrary potential function, which I call it f of t, x t, and x of parents, right? So this is like a local potential where we affiliate with a node, but only involves x of t and the parents of t. And we only assume for this potential function that's greater or equal to 0. When we sum xt for any values of the parents, this is equal to 1. So actually, just looking on the assumption there of this sort of theorem, you can appreciate that in essence I'm going to be showing that this function is a probability, right? Because you say greater or equal to 0, we sum for all the values of xt equal to 1, that means the probability, okay? What we do is we consider all the family of probability distributions, but they're the product of these local potentials, okay? And the theorem basically says that this is first normalized. So if we sum over all the values of all the random variables x1 to xv, this is equal to 1, which is nice. So obviously the individual are normalized, so you expect that this will be the case. And more importantly, this decomposition here, you can show that the conditional of xt given its parents is actually this function that you see there. So basically, if you decompose the joint distribution in terms of some functions that involve only xt and the parents, it comes out that each of these functions is really the conditional distribution, which is what I told you need to remember. Okay? We will see later on when we do undirected graphs, that is not the case, and these functions are way more general, and they don't even have to be probabilities. But right now, for directed graphs, this is the case. And I give you actually the proof, and it looks an extremely busy slide. All right? That's why I want you to type your homework, because guess who was the lazy person typing the slide? My secretary Dolores, which is an imaginary person. All right? So it was me. Okay? Because I cannot imagine asking anybody to type the slide, so it was me. So I want you to build some character by
let me just highlight the proof because you will need to do this for specific distributions in your homework to do things like that. So the first part of the theorem was that if each of these functions is individually normalized, then the product will be normalized. So if we take the product of all of these functions and we sum all possible values of x1 to xv, this needs to come equal to 1. And what I have done is I split the summation on summation terms that have x1 on them only, then x2, then xv minus 1, xv. So I push the summations. This is an operation we're going to be doing very often with probabilistic graphical models. We will build algorithms on this, so it's important to see it. But, you know, this is the only term that depends on x1, this is the only term that depends on x2 and its parents, right? And because the parents come later on, you need to do the summation here, so there can be still parents left there. You don't sum on the parents, you sum on x2, okay? So, when you take the summation and you put the individual sums the way that you see here, you immediately notice this is equal to 1, 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 and theorem is proved. Okay? It is actually this sort of calculation that is going to make operations of graphical models extremely efficient. Okay? The fact that we have these probabilities, these terms that are local in the graph defined in terms of the nodes and the values of the parents means we can do operations local. In this case, the marginalization is a local operation, right? And this allows us to see immediately that this is it's marginal. It is basically normalized properly. And again, it's the decomposition plus the idea here is that we have a topological order of the nodes. And the second part basically of the slide demonstrates that these functions are indeed the conditional distributions of xt given the parents of xt. Okay? And the proof is actually, if you don't hesitate to write down the equation, you know, the proof is trivial. Okay? So what I have done is I want to prove that this probability is equal to this function, right? To this factor. So when I postulate this, I say use any functions like that, take the product, form a joint distribution. Well, I'm going to show now that this, right, is equal to that. And so what I do is I write this as the joint of xk plus 1 and the parents of k plus 1 divided by the parents of k plus 1. And then I calculate the numerator and denominator using the appropriate marginalizations and the decomposition of the joint probability distribution. So I want you to look at the, let's say, either the numerator or denominator and see what exactly I do, you know. Look at the numerator and tell me what is going on there. You know, I write this big expansion, so what have I done? So I had, remember I had, so let me actually back up 1 second, okay? I forgot to mention. We're going to prove that this is equal to that, all right? But I am going to prove it by induction. Okay, I forgot to mention that, okay? Very fundamental. So to prove it for t equal to 1 is not a problem because t equal to 1 has no parent, so basically it's obvious. So we assume that this is a proof for t equal 2 to k, and we need to prove that it's true also for k plus 1 then, okay? So this is the proof that if this is true, then this is equal to that, okay? So when I write the decomposition of the joint probability distribution, I have accounted that from 1 to k, these are the conditional distributions, okay? Because that's part of my induction. And the other ones are the factors. So that's step 1. And step 2 is to get
this marginal of xk plus 1 and the parents of k plus 1, I have to sum over all other variables. And what means is I have to sum on k plus 2 and up to v. And because I have topological order, that doesn't include the parents of k plus 1, which are before k plus 1, right? So I don't have to worry about the parents. And this term I can leave it alone outside any summation because I don't sum on xk plus 1 or the parents. And you notice from here to there, I have to sum all the previous nodes from 1 to k except the parents of k plus 1, which will be possibly maybe xk, right? They're before k plus 1. So look at this again, because this is sort of extremely important, right? Because I'm pushing the summations inside. I have accounted that the potentials up to k, according to my induction argument, they are really the conditional distributions. And then I have this summation of the other factors that I have not proved anything. So it comes out, if you do this, and you do this, on the sort of the denominator, you also have to sum on xk plus 1, because there's no xk plus 1. So this whole big first summation constants, numerator, denominator, this summation constants, and this factorization by definition is 1, because these functions are normalized. So what I get is that this conditional distribution is equal to my factor fk plus 1. So basically, when we said that we can decompose a joint probability distribution in terms of conditionals, the proof is not sort of 10 pages, it's like half a page, okay? Or actually in most books, the proof is considered obvious, so there's no proof, okay? In most probabilistic graphical models. Any questions on this? So there are lots of important things, right? Even though this theorem, you know, our interest is really the decomposition in terms of these local functions that they are conditional of the values of x that is not given its parents. There is some sort of algebra here that is sort of fundamental to the type of things we will do, at least with directed graphs. And the fact that we have a topological order and we can push these summations and do the summation. Can you imagine if we have to sum x1 and x1 appears in all these functions, you're completely messed up. But the fact that x1 is only on the factor here, x2 is only there, right? So obviously, in these problems, you're going to start summing from the right to the left, all right? And we will do lots of examples that you see this. So that's important. And then you notice here some operations to find marginals where we sum up over the rest of the variables. This is sort of a standard operation we have to do with graphical models, especially in the context of inference. So again, I went from the complex problem to the easy problem. I know students like to go from the easy problem to the complex, right? I always like the opposite of the normal case, right? I remember, you know, I said maybe this joke some time ago. I was trying to give a whole lecture on some topic, and some student asked me, can you give an example? And I had not even introduced what the topic was. Okay, you know, so usually in my case I like to give you the theorem and the examples come later, or you do the examples on your own. So here is sort of a trivial Markovian model. So x2 depends on x1, x3 on x2, etc. So what I do is, right, just to apply the theorem so you can see the theorem basically, I say, okay, I'm going to write this as a product of the functions that involve x1 and its parents, which is nothing, then x2 and the parents, which is x1, then x3 and the parents, which are x2, x4 and x3. So then what you can show immediately is that each of these functions, they are nothing else, so the function f3 of x3 and x2 is really the conditional of x3 given x2. And the proof, I take this decomposition, right, and I, you know, to calculate this, I have to calculate the join of x2 and x3 divided by p of x2. So the denominator I have to sum, obviously, to marginalize, I have to sum x1, x3, and x4. On the numerator, I only have to sum x1 and x4. And you can see some of the terms for normalization cancel out, this cancels out, it's 1. And this big parenthesis and this big parenthesis cancel out, and then what I get is f3 of x3 and x2. Just is like a trivial, limited version of the theorem, okay? Again, this concept with functions, right, and these functions turning out to be probabilities is only for directed graphs. We haven't really said anything for undirected graphs. There, things could be way more general. Maybe sort of similar decomposition, at least in the context of this Markov chain, but in general graphs could be a little bit more powerful. Okay, so this is an example from one of the textbooks in machine learning, in probabilistic graphical models. So one of the nodes is the grass is wet. One of the nodes is the sprinkler, which can be on or off. The other one is a node that is raining, which can be on or off. And another one is that it's cloudy. I am assuming basically the dependencies look like that, all right? And if we follow the theorem that I described, the joint probability of cloudy, sprinkler rain, wet grass, all right, is basically written as P of C times P of S given C, P of R given C, P of W given S and R, and immediately you can see by comparing this with the general decomposition using the product rule, which is here, it implies basically two fundamental conditional independence relations, right? And as I mentioned, we will spend maybe a lecture or two where I will give you graph theoretic algorithms to extract these relations directly, okay? So in our case, you can trust that this decomposition is correct because of the proof we did, right? But alternatively, what you can do is you can extract these independence relations, all right? And then from this you can say, oh, that's my decomposition. I mean, in principle, when you work with this problem and you have this graph like that, it means you already have embedded in the graph these independence relations, so this decomposition is automatic. You don't have to prove anything. Okay. If we look at these examples, right, so we are going to need to define this joint distribution. We will need a table that defines the probability of cloudy. So effectively, that's one value, right, because of the normalization. To define this is cloud is false, cloud is true. So if I give you one of these numbers, the other one is 1 minus this number, so I need only one value. Let's say this is the probability of the sprinkler given cloudy. So I am writing this probability when the cloud is a false argument or a true. So how many values do I need to describe this? How many? 2. All right, so I have one value for this, I have 2 for this, I have 2 for this, and if I take this probability, how many values I need? 4, okay? Now, in general, when we do these counts, right, we don't account for the normalization because for a large-scale problem, it doesn't make a sense to say minus 1, minus 1. Yeah, I mean, we can subtract minus 50 on a problem with million variables, it won't make a difference, okay? So don't bother about that. So I'm giving you basically the count for this problem is v times 2 to the k. K is the number of parents per node, and so these are binary variables. That's why you see a 2 there. Actually, I don't know why. The notation is a little bit different from before. Before we're using k for the number of values a random variable can take. Here I use k for the number of parents. Again, you guys are adult and vaccinated, so you can figure out from each slide what the context is, right? So I don't have to go back and change the slides. All right, so that's our big summary there, and I want to be sure that everybody understands what this equation means. All right, that's the whole equation in the course today for directed graphs. Makes a little bit of sense. Really, there's nothing else. Okay? All right. So this is another example, and I think I may have to do this because there is, I'm putting some independence relations for this example as applications in the slides. So this is from Jordan's, textbook to come, sometime in the near faraway future. So there are 6 variables, and based on what we discussed about the decomposition, this is what I have, right? x1, x2 given x1, x3 given x1, x5, etc., x6 given x2, x5. Okay? All right. And you see in this example a nice graphical representation of the tables assigned to these conditional distributions corresponding to each node. So x1, it's a log, x2 is given x1, so it's a table like this, x4 is given x2, a table like this, x6 given 2 values, okay, it's a table like that, and like that. So we're going to have to write actually a little program, I'm assuming, and I'm saying this so should we take notes and to be sure that we assign you some homework problems, but you don't do this by hand, right? You have some little computer program to do this for you. Okay. Don't need this. Don't need this. I already did this. Don't need that. Okay, guys, there's a typo there. How is that possible? I don't like the typo. You know why? Not a very good missing of a letter there. I don't think you guys get me because you never read any newspapers, right? That's the fake news. All right, let's see. This is a repeat, so I'm going to bypass. All right, so let me I think I inserted the slide because it was on lecture 1, and as an application of this directed graphical model, and it's a standard problem that we will see a few times in the course with, for various sort of algorithms. This is the concept of a naive Bayes classifier. So we are not going to do any specific example here, right? But think that you have delta x1, x2, x3, x4 that are derived from, let's say, 2 different Gaussians, but we don't know which Gaussian. Right, so you have one Gaussian, and so we may get the first sample maybe from this Gaussian, the second maybe, and the third from here or there, okay? So y is sort of a hidden variable that tells you each of these x's from what Gaussian is coming. All right? So the idea here is, if I know y, then these samples are independent of each other. And that's the concept of the naive Bayes classifier. Okay? So, so if I know y, all right, these are independent. If I do not know y, then all of these values of x1 and x4, whatever I get, they depend on each other. This is sort of a fundamental problem we will use, in sort of mixed-two models, but many other settings as well. Okay? So you can think of y here, let's say, being a binary variable that takes values 1 and 2. 1 means this Gaussian, 2 means not Gaussian. So if I need a label of y for each x, then these x's are independent. And so effectively, what this is the probability of y times the probability of the bold x given y, and that the probability of world x that includes all these x's given y can be factorized over the data, right, because of this assumption that the x's are independent given y. Okay? So, so this is sort of an important graphical model that goes under the name of naive Bayes classifier. I mean, as a classifier here, you know, I can remove this, but traditionally basically has been this, I mean, the problem is when you say conformal data come, it's like classifying and say they come from Gaussian 1 or Gaussian 2, so that's where the name classifier came. Now, this model, you can sort of introduce some complexity and say these x's are not really independent given y, and you notice on this tree-like graph that you see on the bottom, all right, I started creating dependencies between the x's, okay? So this is what is called a tree-augmented naive Bayes classifier, okay? And you can sort of play around and come up with your own little algorithms. And there is, you know, maybe if you search in the literature, you will find very particular algorithms for modeling these tree-augmented naive Bayes classifiers, okay? For us, right now, I just want you to remember what naive Bayes means, that these future sets given y are independent, so you can have a nice factorization that looks like this, okay? But you can enhance this with dependencies between the x's, and if these dependencies still maintain some tree structure, then you can do easily inference at the minimal cost above what you see on the top. Okay. So as a summary on this missing edge problem and conditional independence relations, on the top I have three variables that they're fully connected, so zero conditional independence relations. Here there's zero connections, all right, so these are complete independence, all right. This is the Markov dependencies. This is sort of a directed tree structure, okay? And we will see sort of what type of dependencies we have this when we introduce the Bayes ball algorithm in about 2 lectures from now. So you can go from something fully connected to unconnected to anything in between effectively. Okay, there is nothing new there. All right. This is sort of, I don't want you to take it in some books, this is listed as a theorem, but I am listing this based on what we have proved up to now, sort of as an exercise, but I want you to look at it because, in essence, this equation on the top takes a directed graph with v variables and provides a very general decomposition around this node xv for an account for the parents of node v, the non-descendants, and the descendants of node v. So I want you to don't read what it says in the proof. I want you to look on the equation on the top, think of the product rule of probabilities, and tell me what is the only fundamental equation that accounted to derive this thing at the top. So basically, you know, this is the product rule, right? So I am actually, I'm starting with the probability of the non-descendants, and then of the parents given non-descendants, of V given the parents, and then the descendants given V parents and non-descendants. So this looks like a product rule except this blue term, and that blue term, what should I have in the, what is going on? Let's see, okay. What should I have in the dependency there for this to be the full product rule that is not shown because of the independence relations? When I write as x of the non-descendants, then I have the parents given the non-descendants. So here I have x of v given what? What should I put here? Given the parents and the non-descendants. And the fact that I don't have the non-descendants is because we already have proved, right, but given the parents, B is independent of the non-descendants. So the idea here is, I can come up with sort of decompositions like that, all right, that are very general, okay? But the bottom line is, you don't need to know any of this except the product rule and the fact, the fundamental property for directed graphs. But if you want to see sort of a proof of this from scratch, to convince yourselves that actually, again, the whole thing fits in, you just have to use this marginalization that we did in 2 examples before, and then you can prove that this decomposition is correct. Okay, so I'm going to take an example, right, again, to emphasize on how you prove these independence relations. But let me tell you, I'm going to prove them in a way that involves algebra, but the whole purpose of learning probabilistic graphical models is not to ever have to do that algebra. In other words, the whole purpose of probabilistic graphical models is to learn these independence relations from the graph itself, independent of the distribution. But now we're going to go the long way because we haven't studied yet how the graph implies independence relations. Okay? So I take this graph, all right, and we already have decided how the probability of the 6 variables decompose in that graphs. And I'm stating here all the possible independence relations that you can have. Okay? I know what, from where they come. So for this lecture, I'm going backwards, right? So I'm saying these are the independence relations. So, for example, if you want to prove that given x2, x4 is independent of x1 and x3, again, given x2, x4 is independent of x1 and x3. All right? It's not obvious. I mean, we haven't really said anything, but this is an independence relation fundamental to this graph. Given x2, x4 is independent of x1 and x3. So to prove all of this, you will agree with me that it's sufficient to prove that this probability, all right, is equal to what? Look carefully. All right, so given x2, x2 is there, x4 is independent of x1 and x3, and there's no x1 and x3 there. So will it be sufficient to prove this equal to that? Right? So the long way, which we will never do after maybe lecture 2, okay, is to prove that this is equal to that. You write this as P of x1, x2, x3, x4 divided by P of x1, x2, x3. You plug in, I'm actually, okay, I wrote that this x1, x2, x3, x4 is that. What happens to x5 and x6 here? I don't see them. What happened to x5 and x6? Well, I mean, if you look at the equation at the top, to get this marginal, when you sum on x5 and x6, this is equal to 1 and this is equal to 1. So they disappear. You see that? When you marginalize in the joint on x5 and x6, because these are conditional distributions, the summations give you the identity. Okay? So really this is the joint of x1, x2, x3, x4. And then if you want the joint of x1, x2, x3, you have to sum in x4. But when you sum in x4, this will disappear because summation of x4 will give you 1. All right? And then this cancels with that, this cancels with that, and then what you get is P of x4 given x2. Okay? So this is how you prove these independence relations. But I want you to remember the idea is not to do this algebra and all of this and say, oh, there is an independence relations, but to have an algorithm that looks at this graph and it says this graph implies all of these independence relations. So you know that every distribution that factorizes on the graph has to automatically satisfy all of these relations. Okay, that's the whole idea. So we're not going to do the heavy algebra, but we will need an algorithm that using sort of graph arguments, it points immediately to what these relations are. And here is another independence relation. X1 given x6 is dependent of x2 and x3. A little bit on the notation that maybe I haven't emphasized in all the graphs when you condition things, right? This is like your evidence, like if you knew x2 and x3, and you know the things that are conditioned in the graph, we mark them with dark color. All right, so this means that's the evidence. If I knew those, you know, if I knew those, then x1 and x6 are independent. I copied and pasted against this from slide 1 because I'm going to show you the different ways of looking at the directed graph. So, imagine that X is, in this case, a disease, let's say cancer, and Y is some outcome of the disease, you know, some abnormality in the blood or other things. So Y is derived from the disease, right? But you may have many X's, many diseases, and you have a symptom that can be derived from many diseases. So you can see this as a mapping from X to Y, from a disease to an outcome, but also you can see this as an inverse problem, where if you have an outcome from, let's say, a blood test, you're asking, what disease do I have? And so this graph that you see in this picture, in this case, you know, I'm writing this as sort of a generative model, the join of X and Y, as the probability of X times the probability of Y given X. So when we implement this, you know, the probability of X, maybe we define it by how many people in a population have cancer, all right? So you can use population statistics to come up with P of X. And P of Y given X is really the forward model, all right? So because X causes Y, right, P of Y given X really follows the direction of the arrow the way that you see it here. Now, if you do the inverse problem, even though the arrow is written from X to Y, really what you're asking is, if I measure Y, what is X? So you're asking for the probability of X given Y, and the way to calculate this, because this is really what you know, so the only way to calculate P of X given Y is using Bayes' rule. Okay? So look, for the students who have not taken the class, you know, in the fall, you know, this is a sort of a trivial application of Bayes' rule, right? But in some sense, when somebody looks at this, will think that actually this graph sort of in the directional setting is not appropriate, because you're saying, if I know Y, what is X? So somebody would say, no, maybe the arrow should be the other way around, right? But that's not the case, because you know what? X causes Y. I mean, there's nothing that we're going to change in this. You know, Y doesn't cause X. So the causality relation is from X to Y, but that doesn't mean you cannot do inference, measure something for Y and say what is X. Okay? All right. Actually, if I remember the next two slides, when we discuss this independence relations, we will talk about this extensively because it's a serious problem with directional graphical models. But let me take this problem with the sprinkler and the rain, you know, that we discussed before, okay? So the way you can use this graph, you can go from causes to effects. So for example, let's say we observe that it's cloudy, and then you can ask, what's the probability that the grass is wet if it's cloudy? Well, actually, you go, again, you go from causes to effects, okay? And that's why this is, you know, what I would call prediction or uncertainty propagation in the forward manner. You propagate uncertainty in the graph. You go from cloudy to wet, okay? So this is from causes to effects. That's these are the problems you can solve. Now, from effects to causes, this is what is called a dimensional reasoning, or diagnostics or explanation. Is the following problem. I observe that the grass is wet, and I want to figure out what caused the grass to be wet. Right? Is it the dog of the neighbor? You know, or what? Okay? So, for example, let's say two problems you can pose can be the following. You may ask, what is the, given that the grass is wet, what's the joint probability of the sprinkler and rain, okay? And maybe we're interested in the maximum of this, right? So what is, let's say, the maximum probability that the sprinkler is on when it rains, okay? Or we ask, for example, given that the grass is wet, is the probability that it rains higher than the probability that the sprinkler is on? Right? So notice I go from effects to causes. From effects to causes, okay? So this is the inverse problem. Given some evidence, I want to figure out what causes that. Right? And that's really the main task in Bayesian inference, right? We want, using some observation, some evidence, to figure out what causes that evidence. So let me pose a problem that, it's a fundamental and tricky problem in graphical models. And again, this is just to give you a heads up on the topic. So let me ask you the following question. Do me a favor, don't read this because you will be sort of brainwashed and then you will tell me you got the answer. So here is what I am asking. I know that the W shows the wet grass, right? So I know that the grass is wet. Think the following. If the grass is wet, is the probability that the sprinkler is on bigger than the probability that the sprinkler is on if I also have observed that it rained? So in other words, is this less or bigger than that, and why? So I know for sure that the grass is wet, but on the left-hand side, I also know that it rained. So what exactly happens? So I'm just telling you that this inequality is correct, but what exactly is happening that leads here to this being less than that? Huh? Yeah, but what's the relation of W and R here? Or what's the relation of R and S? So basically the sprinkler and the rain, right, can explain the wet grass. But the fact here that I have evidence that it rained, all right, that takes the probability that the sprinkler is on away. It has explained why the grass is wet. The grass is wet because it has rained. So effectively here, only one of the parents of W, all right, takes away, it explains the effect of the other parent. And this is sort of a very tricky thing that only directed graphical models can account for. When we do undirected models, we have hard time sort of to introduce this concept. So this causal relation is fundamental to graphical models, and it is sort of something we need to carefully account for, okay? So again, I observe this, if I observe that, it takes away the probability that the sprinkler is on, because this has already explained that the grass is wet. Okay? We will formally see this with a derivation, okay? But in essence, if you appreciate this example, all right, we will be able to advance, rapidly with no problems in maybe in a lecture or two from today. Here's another example with the same problem, all right? This phenomenon, by the way, is called explaining away. It comes with different names. Let's say you have two coins. These two coins are marginally independent, right? You can heads, whatever outcome you get doesn't depend on anything, so they're two independent coins. Let's say this is the sum of what you get of the 2 points, all right? So if somehow you observe this, and you observe one of this, so let's say if the one coin, let's see, 2 coins, the variables are binary 0 and 1, all right? So let's say that this outcome is 1, and suddenly we observe 1 here. All right? Then immediately, this, it has to be 0. Okay? So this has explained away this, all right? So this is sort of the explaining away phenomenon. I'm actually proving this, in the slides, using, again, the factorization we introduced. You can actually compute the marginals and do the algebra, nothing major. So this is the factorization we started. So you can actually prove all the equations that you saw in the previous slides. My eyes got this relation, so let me just say what's going on here. So remember we said that x at any node v given the parents independent of the non-descendants. Okay, so here grade depends only on given the parents basically. The grade is independent of anything else. Okay. The SAT score or what grade student got, etc. But I look at this equation on the bottom, okay, and it says, given the intelligence of the student and the difficulty of an exam, all right, G is independent of L, okay, that's not what I wanted. Oh. However, information about this descendants. Well, so let me just read the sentence, okay? It's not written with an equation. Any information about the descendants can change beliefs about this evidential reasoning process. So in other ways, if you know what letter the student has gotten, okay, it changes the picture, okay? Because right now we look what causes the grade, and we say it's the difficulty and the intelligence of the student. Right, so if the evidence is the difficulty of an exam and the intelligence of the student, that grade is independent of anything else, but if I collect information from below, that needs to be accounted in the picture, okay? So we will see this sort of problem when we discuss independence relations and evidence. Okay. Right. So let me, I only have 2 minutes, right? So let me refer to this equation and we'll come back in next week. So you can think a very general directed graph, and what I have done is I have split the variables in the nodes of the graph to visible variables. So you can think this is the evidence, things that I measured, and else are the hidden variables. So fit are parameters in the model. So you can think, for example, if you try to compute this conditional distributions on the graph, and you don't know what their values are. So this may be unknown parameters that you have to calculate, okay? And we will discuss this extensively in the course. But here what I want to tell you is the main inference problem in the graph is to compute the values of the hidden variables given the visible variables. And the way basically we do this is using Bayes' rule, so the numerator requires the joint distribution, and this will be the factorization that we get on the graph, and the denominator is basically the joint distribution where we have sum up over all the hidden variables xx. Okay? So again, these are the visible variables, these are the hidden variables, and this is sort of the main task that allows you to calculate these hidden variables. Now, the other thing I was going to say, we say theta is also a hidden variable, but here I use hidden variables to be variables that grow as the number of data grow. So you can think, you measure a value of a random variable, but you don't know from what Gaussian is coming. So the hidden variables can be maybe indicator values that tell you what each data point you collect to what Gaussian it belongs. Are we too late or what, okay. So the idea when I write this decomposition is, right, that these hidden variables go with the number of the visible variables in the graph. You can keep the door closed, please. So these parameters theta are independent of the data you collect in the problem. Okay, so and in many problems in probabilistic graphical models, we're going to be able to actually use a point estimate for the static parameters theta, but this variable x can be millions, right? As you collect a lot of data, so you really need to be able to do sort of calculations. You need to carefully account for the fact that the number grows, and somehow when you do calculations, you may have to do predictions by integration of these hidden variables from the model. Okay? So, all right, I'm going to finish there. I'm going to come back again just to give you an idea on how we're going to be computing later on this parameters theta. So, summary. Recitation for those who want on Friday. There will be a homework posted tomorrow. It's not going to be due until a few weeks from now, but you can start working on it. And the video lectures are directly linked on my website, at least the previous one. And the slides are already up there. And I will see you on next Tuesday, I suppose.